All right. In this problem, we're going to just remind you that we're doing another work problem. Work is done by a variable force, Fx, in moving an object along the x-axis. It doesn't have to be along the x-axis, just calling it x-axis. Has this form. So W is equal to the integral of the force times the displacement. Okay. So that's our general notion here. And so here, our problems that we're going to consider is the following. So the canonical tank is filled to the within 2 feet of the top with olive oil weighing 57 pounds per cubic foot as its density. How much work does it require to move or to pump the oil to the rim of the tank? Okay, so that's the setup or the thinking about the question. So imagine this is our canonical tank here. Okay, so it's a cone, right? And the relationship of the cone is the line that defines the cone has an equation of y equals 2x. Okay, and so what we're trying to consider is the height of the cone is a total of 10 feet, and it filled all the way up to within. So this is the very top layer. So the distance from here to here is 2 feet, which means that there's 8 feet below of this oil. Okay. So there's 8 feet of this oil. Okay. So we're just going to choose an arbitrary location and consider a small slice perpendicular to the y-axis. We're going to assume that the force acting on the oil is only the force of gravity. Okay. So if you can imagine like a little oil droplet in this being suspended in this fluid, okay, then what's pulling down on it is the force of gravity. Okay, the force of gravity is pulling it down. It's the mass times the gravity times. But since this is a fluid, what we're going to have is rho v times g, where the mass is the fluid, the density of the fluid times the volume that the fluid is holding up. Okay, so that's what we have to figure out and consider. So we have all these little particles in this, and so we're going to consider an arbitrary volume. And because of the geometry of the problem, if we make our vertical height an infinitesimal amount, an infinitesimal height, what we find is that we're going to have a bunch of these little cylinder looking things, and so we can figure out the assuming a uniform volume or density, of course, that we can figure out the essential force of gravity acting on this volume, and then we can figure out, well, what will it take to move this infinitesimal disk of volume from this position up to the rim of the canonical tape. Okay, so that's kind of the thinking or the idea behind it. And so you can see that this cylinder with an infinitesimal, so it has a really tiny uh, height to it. Um, and have the radius. Well, the radius for us, we're going to have to convert from y equals 2x. We're going to solve it for x, so that way we can get the height of or the radius, if you will, of the cylinder in terms of its height x. Okay, so the area then is really what we're going to be looking for. So this volume delta v is going to be pi r squared. Okay, so that's going to be the area times the height, which is delta y. So this is the area of a circle times the height. Okay, so this is going to be the delta v here, and I'm calling it delta v because I want to keep in mind that it's a really small volume, and we're talking about a very small change in the volume. Okay, all right. So this is the first thing that we're going to have to figure out. Okay, so once we know the volume, and then once we know the volume, this delta v, we know the density that was given to us, and we know the force of gravity. Okay, so those things will be given to us, and then we just have to figure out the vertical displacement, and then integrate over that displacement to figure out what the total force will be. It's kind of the big pieces to the problem. Okay, so let's go ahead and dive in. So we have most of this already kind of figured out, as I mentioned. So the radius of the disk is the 1/2 y, and that comes from the fact that from the y-axis out to this point, this disk has a radius equal to the x value of this height. Okay. So we're going to plug that in. So we have pi y over 2 squared is the radius, and then the um, delta y will be the infinitesimal height. It's just a small change in height there. Okay. All right. So if we simplify that, what do we get? Looks like pi over 4y squared delta y. Okay, so this is the volume, delta v. All right, and so now we need to figure out, okay, we're gonna move this volume and we're gonna keep it times the density. So I'm just gonna call the Greek letter rho is the density, the number, the symbol usually for density, like I used here. That's going to be equal to pounds per cubic foot. Okay, so I'll just keep it in terms of rho because I don't want to keep writing all this and just writing one thing is easier than writing all that. Plus, I like to kind of keep things in general before I start plugging in numbers. Okay. All right. So what is our force? Our force is going to be rho or delta V times V. Okay. Um, well, I can keep throwing in the G. The density includes the force of gravity in it. So actually, we don't need the G on each of these. So I kept feeling like that didn't feel right. The units weren't working out. So I had to pause and confirm that that was the case. So yeah, so the force of gravity is in the density, so we don't have to incorporate that. The fact that the units are pounds, that's the unit of force. So we don't need force in a force. So the force being acted on the fluid is rho v. Uh, this is the volume displaced, and that's the density of the fluid. Okay. All right. So then we have to figure out the distance that this thing is going through. Okay. So we're going to move this infinitesimally thick, this disk, if you will, of fluid, this height up. So it's moving from wherever this disk is located between the 8 feet height and the bottom of the canonical tank. And so we know that the total distance is 10 feet. Okay. But the height of the disk is y feet above the origin, which we're taking to be at the tip of the cone here. Okay. So how far does the disk have to move? Well, the disk distance depends on its height y. So it's going to be the difference between 10 and its height y. That's the distance that it has to move upwards. So the the force times the differential distance, okay, is going to be, and this is a differential volume on top of that. Okay, it's going to be, I guess it's not the differential distance per se because the differential is in the height, but the differential distance. I don't like that. I'm not going to say that. So that perpendicular distance or displacement to be moved. There, I feel better. Okay. So then I should really call this EF, and this should be really like a dV. Okay. Especially in the limit as I add up all of these things. So then then the work done is going to be equal to the integral. The integral from 0 to 8. So the limits of integration are over where is the volume occurring at, right? Where is this liquid occurring at? Well, the liquid is only between the heights of y equals 0 and y equals 8. Okay? The distance it moves is taken care of in the fact that we have this value over here. Okay, so we're going to have rho. The v was pi over 4y squared dy. That was the differential volume. And the distance it moved was 10 minus y. Okay, all right. So start plugging all the information in. And rho is a constant, this is a constant. So we're going to have rho pi over 4. And go from 0 to 8. What do we have? Y squared. That's 10 minus y dy. So distributing this into each term, and then using the power will probably be the most direct method. So rho pi over 4. Um, I will write it out just to be clear. Y 10y squared minus y cubed dy. Okay. So you get rho pi over 4. Adding 1 to the x1 and dividing by it, it's going to give us 10 thirds y to the third minus 1/4 y to the fourth. And we're going to evaluate both of those between 0 and 8. Now, notice that both of these have a y value in it, and when we plug in 0 for both of those, the bottom limit will just disappear. So we don't have to really worry about plugging in that. We do have the 8 to plug in each one. I also notice that here I have a y to the third in both of these. Okay, so for plugging in purposes, just to make it a little bit simpler on me, I'm going to pull this out as pi over 4 rho y cubed. I have a 10 thirds y. Nope, that's not. Minus 1/4 y from 0 to 8. Yeah, okay. So now I can plug in that pi over 4 rho 8 cubed 10 over 3 minus 1/4 8. What is that? 2? 10 thirds minus 2. So 10 thirds is 3 and 1/3 minus 2. So that's going to be just 1. Mm-hmm. So it's going to be 1 1/3, or better known as 4/3. Okay. So 8 cubed is, so try to simplify this. I was trying to fit it on here, but it looks like I'm gonna have to concentrate a bit. So now pi over 4 rho 8 to the third is 500 and I think it's 12. Is that right? Plug it into the calculator and yeah, 512. And then we have the 4/3 here. Okay. So this is nice because the fours will cancel out. Let's see, this is divisible by 3. We have 5, 6, 7, 8. So no, so 3 doesn't go into that evenly. So it looks like the final answer is going to be 512 pi over 3 times the rho. And the rho for this was 57 cubic or pounds per cubic foot. So the volume, we get the volume here. This is the volume in cubic feet. We multiply that by the density here. That would give us then the 512 pi over 3 times 57 pounds per cubic foot. And this is the volume in cubic feet, so those cancel out. And so this product gives us the amount in pounds. And let's see. So plugging that in the calculator, I'm getting it's about 30,561 pounds of by foot pound. What? There should be a extra value of the pounds up there. Units are important, so keep track of them. I missed one from the cube. Okay. All right, so this is the amount of work required. I like it. I would like it maybe a little bit more exact answer, but either way, I hope that was helpful, and I'll see you in the next video.